Welcome friends to the video number 3 for the formulation of the video stiffness matrix for CST. Now in the previous two videos we have defining the two formulations. One is for the psi function and the another one is the stress function. Psi function is a displacement function and the sigma functions, that is the stress function. So that two formulations we have carried out. Now let us move on the step number 3, that is deriving the element stiffness matrix. So now this is the main factor or the main process, element stiffness matrix. Now whenever we are designing the element stiffness matrix, we need to use the principle of the minimum potential energy. Now what it suggests, that minimum potential energy. So minimum potential energy, that is minimum potential energy is equal to potential energy, that is ui vi vj multiply, that is d matrix. So that my total potential energy is equal to u matrix, that is the strain energy minus this is not the plus, this is the minus, that is ohm b, ohm p and ohm s. Now what is that? U is equal to strain energy. Now ohm b is the potential energy of a body, b is body force, then the potential energy of the concentrated load, and the third term is the potential energy of the distributed load. We have already seen that. Now this is the element. If this element is applying with this force, this is the point load, but when there is a traction force is applied. So traction force is applied on a edge. So whenever we are applying the traction force, then a that is called as a potential energy of the distributed load or the surface traction, and the body force is a different issue. So that one is the potential energy of a body force is considered here. So strain energy is equal to 1/2, that is the integration of a volume means dx dy dz, strain energy, transpose of the strain energy multiplied by stress energy. So this strain energy matrix also we are finding stress energy, or the stress also we are finding. So these matrices we have already find out. So that is u is equal to 1/2 triple integration of volume, that is E transpose into the my this sub sigma value, but this sigma value is converted into a constitute matrix multiplied by my this matrix, that is the strain matrix. Again this D transpose is equal to D, I am writing here. So that this is the strain matrix, hence the potential energy, hence this is the my U matrix, or this is my strain energy. So this is the formula for my strain energy. Now the potential energy of a body force. So potential energy of a body force means that is the weight. So again this is the minus, because u minus all these stresses. If whatever the value comes, according to that we could say that material, that element is safe or not. So minus that is equal to triple integration of xi transpose into the x into dv. So xi is my general displacement function. This one is already we have derived in the video 1. Now x is the body weight per unit volume, or we could say this is the weight. This is the weight density matrix. Then the potential energy of the concentrated load, that is a point load. So concentrated load is equal to minus D matrix into P matrix. D matrix is the nodal displacement and P is the concentrated external load. So if there is a concentrated load, means the single load is applied. So this is the matrix for that one. Then the traction load, then the surface traction loads. So whatever the traction forces we are applying for that one, traction force is equal to minus double integration. This is the traction force is applied on a surfaces, it applied on a surfaces. Since this one is applied on the surfaces, so this is not the integration of a volume, but it is the integration of a surface. So surface multiplied by psi function, that is my displacement function, multiplied by my traction force, my traction force at the ds, at a ds. Hence this one is the integration of s psi transpose into T matrix. So where T matrix is the surface traction, T matrix is the surface traction. So finally we are knowing that this one is the psi s, that is the field of the surface structure through the surface traction act. Hence my psi s is equal to my shape function, surface shape function multiplied by my displacement function. So psi is equal to n shape function multiplied by displacement function. So this is the shape surface matrix, shape function of the surface matrix. This one is to be calculated. Then hence pi p is equal to that is one half triple integration of a volume, then D matrix into B matrix into constitute matrix. This is my strain energy minus my weight my weight minus point load minus my surface traction. So this is the strain energy, so this is my strain energy. So this is the matrix, this one is the term comes from my strain energy. This one is already derived. This one is my weight, this is my weight. This one is this one is this one is my point load, this is my point load, terms comes from the point load. And this one is my traction load, this one is my traction load. So this, from this traction loads what we are getting now, this one pi p is equal to strain energy is equal to volume, then displacement matrix multiplied by B transpose matrix multiplied by D constitute D matrix, which one is related with a plane stress plane strain condition, then again the B matrix into D into V plus volume because this is the weight, D matrix into N transpose into X into dV, then the point load D matrix into P matrix, and the surface traction, that is the double integration of D matrix N matrix T matrix into ds. Hence hence we are able to get this total equation, that is in terms of the shape. So here we are getting this one. Now this is the D matrix. Now this one is the volume, again this one is the what, this is the volume. Weight matrix is converted into the shape function, so shape function matrix into X, this is one. Then the point matrix, here again the surface traction is into the shape function matrix, traction into ds. Hence finally we are moving forward, and later on we are calculating the solution in the video number 4. Thank you for watching.